Hello, chemistry, and welcome to our new lesson. Today we're going to learn about Avogadro's principle, or sometimes called Avogadro's hypothesis. And Avogadro's principle essentially relates the volume of a gas to the number of moles N of the gas. And it's pretty succinctly stated in the chorus to the song that I have posted along with this link, and that is the Amadeo Avogadro song. And the chorus goes, equal volumes of gases at the same temp and pressure have the same number of molecules. Now, what that's really telling us that if we keep temperature and pressure constant, those are the two things that are going to be constant now, that the volume of a gas is directly proportional to the number of moles of gas. This is going to be a direct proportion. And we saw this in our simulation where we had a balloon blowing up. And basically, as we saw in the balloon, and relating this all to kinetic molecular theory, as the number of molecules in the balloon goes up, that makes the force in the balloon go up because the number of collisions on the inside of the balloon is going up. Remember, the number of particles is also going up. Now, we did say we wanted to keep pressure constant. So to keep pressure constant, the area or the volume, the denominator, also has to increase by the same factor. So if the number of molecules doubles, the area is going to have to double. So the area is going to have to go up in order to keep the pressure constant. So because this is a direct relationship, we have that as N goes up, the volume goes up, or as the number of moles goes down, the volume goes down. Usually we think of this as a response to how the volume responds to increases in the number of moles of the gas, as in with a balloon. But you can turn it around the other way. And with the syringe that I've been using, and I might show this in class just to demonstrate it, you see that as you increase, if I take the cap off the syringe to allow gas to go in and out, if I increase the volume of the syringe, more gas is going to go in to keep the pressure inside and out the same. So now, since N and V, or V and N, are directly proportional, we have that V divided by N is equal to some constant. Again, this constant is not important, but we can rewrite that thinking in terms of the Boyle's law, Charles's law kind of relationship, that V1 over N1 is equal to V2 over N2. And you will use this relationship for one or two homework problems, but this is not the way we typically think about Avogadro's law problems. Instead, what we're going to do is set up what we call a molar volume of the gas. Now, anytime you see that molar volume, you see something called molar, that means whatever something is for 1 mole of whatever you're looking at. So in this case, 1 mole of a gas. And STP is a special set of temperature, standard temperature, and pressure. I guess we could say special, but a standard temperature and pressure, which is an easy set of conditions to achieve in the laboratory. So standard STP, again, standard temperature and pressure. And those conditions are the temperature is 0 degrees Celsius or 273 Kelvin, and the pressure is 1 atmosphere. And it's very easy to achieve both of those in the lab. And when you have those conditions, the volume of the gas is 22.4 liters. And you know what? I'm going to put it per mole there just to show you that it is per mole. Although when I said 1 mole of a gas here, that means the same thing. So we set this up that V over N is equal to 22.4 liters over 1 mole. And that's going to be the molar volume of the gas at STP. We're going to use that as a conversion factor. And so our conversion factor is going to say, excuse me, 22.4 liters per mole. And this is on your reference packs, so you never have to memorize it, but some of you may start memorizing it, start remembering it anyway. So what this is going to help us to do now is relate volume and moles of a gas in mole to volume problems. I can give you a nice simple problem. I give you 4.20 moles of argon, and I want to know, here's my question mark, what's the volume? And we're going to have liters as our answer. And I'm setting the condition at STP because in our next lesson, we're going to learn how to deal with conditions when we're not at STP. So the volume of the gas, the liters of the argon, start off with our given 4.20 moles of argon. And then we're going to multiply that by our conversion factor. We want the liters in the numerator, so 22.4 liters of argon in the numerator to cancel out the 1 mole of argon that goes in the denominator. That leaves us with liters of argon. You should stop and do this problem on your calculator to make sure you get the right answer. And when you do that, you should get 94.1 liters of argon as your answer. Now, we're not always given nice moles of argon and moles of the gas. Often we'll be given the mass of the gas, and you should always remember that if I give you the mass of the gas, you can always get to the moles of the gas. Remember, moles to mass, mass to moles is pretty easy to do. The conversion factor, molar mass, and of course, you'll have to be given the gas as well, unless I'm asking you to calculate the mass of the gas or what the molar mass is. And in this question, I'm asking you to tell me what the mass is in grams. And so you're going to calculate the moles first. And from the moles, then you can get the mass in grams. So if you want to stop the video for a moment and see if you can set this up, then go ahead and do that. Otherwise, follow along, or if you're coming back from that, follow along in how we set this up. So we want to know the mass of the gas in grams, so that's our question mark, mass of O2 gas. And we're starting with 36.6 liters of O2 gas, again at STP. So that means we can use our conversion factor. But now I need to put the 22.4 liters of O2 in the denominator so I can cancel those out and have my 1 mole of O2 in the numerator. And from here, we're going to go to the mass. We're going to cancel out the moles of O2, 1 mole of O2 in the denominator. And we need the mass of O2. Don't forget that O2 is diatomic. We need 2 oxygen atoms. So it's 32.00 grams of O2. Cancel out the moles of O2. And if you haven't done this calculation already, stop the video to do so. And you should get 52.3 grams of O2 from 36.6 liters of O2. Okay, so you now have enough material to do the next homework. So please go ahead and do the next homework, and I will see you in class the next time.